Hello, it's Keith here, and this is lesson 61 of the platform-specific series of my Z80 programming tutorials. Today we're going to be looking at the Amstrad CPC again, and we're going to be looking at a little trick I was playing with a while back, which is 2 and 4 times sprite scaling. You can see an example of it here, but we're going to see it in the real code in just a moment. Now this is going to be done with a lookup table, and the lookup table is going to contain the values for converting the byte data into the converted pixels so that we can very quickly scale a sprite. Now essentially it's not going to be much slower than drawing an unscaled sprite at the same size. It will be a little bit slow because of the lookup table lookup, but it won't be as slow as calculating every pixel would be, which would be totally unviable. Now the idea of this is it will allow us to have very big sprites on the screen without taking up lots of memory. So if we had a scene where a character was zooming close to the screen, for example, we could use this as part of that scaling without having to say very large sprites. Of course, if you had a very big enemy and you didn't want to store that as a bitmap because you didn't have enough memory, you could again use this to make a very big object by scaling up. So we're going to be looking at this. We're going to be looking at it on the Amstrad CPC, but the principle will work on any system where you have direct bitmap access. So tile sprite systems couldn't be done like this, but a system like the Spectrum or the Sam Coupe could definitely do this in the same kind of way. Okay, well, let's go over to the code and let's see what we'll be playing with. Now, today's example will work in mode 1 or mode 0, so the 4 color mode or the 16 color mode, although the sample sprite is actually only going to be 4 color in both cases. Now, the sample bitmap we're using is in exactly the same format as the simple series one. It's the same bitmap, and the scaling routine, the one-time scaling, the unscaled, is almost identical. It's just the registers have been changed so that it matches the 2 and the 4 times one. We're using the shadow registers as extra registers basically because we need a few extras for the scaling routine. So here we go. Here's the 3 versions. So you can see on the left here, this is the unscaled version. So this is the 1 times version. This is the 2 times scaled version, and here is the huge 4 times scale version. And you could see there it was pretty quick. I'll just run it again. So there we go. So even though we're effectively real-time scaling this sprite, it's pretty quick. Now, I say real-time scaling because, of course, we've got to allocate some memory for the lookup tables, and it's quite a bit of memory we're using. But if we had lots of sprites we were doing this with, it would be definitely worthwhile. And this huge sprite here is going to be covering about an area of about sort of 8K here. So very big if we were saving that as an unscaled sprite. So as I say, interesting trick I think here. Now that's the mode 1, which is the 4 color mode. Mode 0 is the 16 color mode, and this example will run on that as well. So if we just run that. Now the sprite is going to be chunkier, of course. You can see it's half the horizontal resolution. That's the way the CPC works. And then it's scaled up as well, and that works just fine. Now, the mode 1 version has 2 lookup tables, one for the double size and one for the 4 size, and that's because there's 4 pixels per byte in the unscaled format. The mode 0 version only has 1 lookup table, and that's for the 2 times scale because there's just 2 pixels in each byte. So when we want to scale 4 times, we're actually using the 2 times lookup table and writing each byte in that twice. Now, what those lookup tables contain, we'll learn in just a moment. Okay, so let's have a look at the code and we'll discuss what's going on. Now, here we are, first of all, starting up and we're enabling our screen mode 0 or 1 here, just depending on if this mode 0 is set here. And the first thing we're doing here is we're running this build lookup tables routine here, and that is defining the data that we're using to quick scale the data. Now, before we actually look at that, let's look at how we're actually drawing the sprites. So we've got this getScreenPos function, which is basically the same kind of thing as we've seen many times before. It's calculating a destination screen address from an XY position. So we've got the positions for our 3 tests here. We've got our source image, and of course it's the same image in every time because it's the drawing routine that is scaling up that image. And the image is the same image as we've used in the past in the simple series, and it's just exported with my AccuSprite editor. So nothing special about the image at all. All the work is being done by the doScale routines. So here's the unscaled version. We're loading in a byte from HL, writing it to DE, we're repeating until the line's done, moving down a line, and then we were just repeating until all the lines are done. So we're drawing our entire sprite to the screen. Now that's what we'd kind of expect. Reading from HL, write to DE. Now, when we want to scale our sprite, we're using a lookup table. And you can see things have got a little bit more tricky here, but we'll go through it bit by bit. So what we're doing here is we're loading BC with the address of the lookup table, and this is the lookup table for a 2 times scale. What we're then doing is we're reading in a byte from the source, but we're loading it into C. So now BC points to an entry in the lookup table which corresponds to the source byte. Now, what does that entry contain? Well, what it contains is the first scaled byte for the screen. Now we're taking a 1 byte piece of data and we're scaling it in twice, so it's now double the width. So what we're doing now is we are going to write 2 bytes to the screen for the 1 byte that we read in, and that's what we're doing here. So BC points to the first byte scaled in our lookup table. So we're reading in a byte from that and then we're writing it to the screen. We're then increasing the screen horizontal position and we're incrementing B. So C is the byte we read, and we've got 512 consecutive bytes, with the first one being B and then the second one being B plus 1, that are the scaled version of those pixels. So what we've done there is we've done the first one, we then increment B, and now we do the second one. We then decrement B to get BC back to the same position as before. Now C will be overwritten when we read in the next byte, but that is effectively getting the 2 destination bytes for the unscaled byte that we read from the sprite. And it's the lookup table and the format of that lookup table that's doing all the work. Now this is all relatively fast because really all we're doing here is we're loading in an extra byte from memory from the lookup table here, and we're doing an increment of B and a decrement of B here, and that's really all that's changed compared to our unscaled version here. So it's not too much slower. Now once we've done a line, we're basically having to repeat because we're doubling each line as well, because we're scaling not just horizontally but vertically. Of course you could change this. You could have a version that scaled horizontally and not vertically, or if you wanted one that scaled vertically but not horizontally, but you wouldn't need the lookup table for that. Now this routine will work for mode 1 or mode 0. It's the contents of the lookup table that defines the mode it works for, not the contents of this routine. So that's the 2 times version, and the 4 times version is almost the same. We're just using a 4 times lookup table this time for mode 1 because there's 4 pixels per byte. So when we scale our byte up 4 times, we need 4 converted bytes to write to the screen to scale it up 4 times. Now in mode 0 we don't need 4 because, as I say, there would only be 2 pixels per byte, so we can write each byte twice and that will allow us to do the scale up. So we've got our lookup table here. We load in our byte from the source sprite again here, and then we are going to write 4 bytes to the screen here. 1, 2, 3 and 4, and each time we're incrementing B in mode 1. Now in mode 0 we're only incrementing B once. Here we're incrementing it twice if we're in mode 1, and that's because, as I say, the 2 times lookup will effectively do the job. We just write each entry twice and only increment the position in the lookup table twice, increment B of the position in the lookup table. And that's doing our scaling there. So that's the 4 times version there. And of course, if you wanted to do an 8 times version, it would be a huge sprite, or you might want to do that. If you wanted to do that, you could use the 4 times lookup table in mode 1 or the 2 times lookup table in mode 0. You just need to double up the number of times you wrote each byte that you read in from the lookup table. So again, this is the equivalent. It's basically the same as the 2 times version, just using the alternate lookup table and doing twice the increments from the lookup table and writing those to the screen. So it's actually the lookup tables that are doing the bulk of the work, and that's the point. That's why it's so fast. If we were splitting up each byte into pixels and shifting those pixels around, it'd be very slow, and we are effectively doing that shifting, but we're doing it for every potential byte that could be on the screen, and we're creating a lookup table for all 256 bytes. Let's have a look at how we build those lookup tables. Now, we're defining 2 lookup tables here, and because of the way we're doing things, if you think of the 16-bit address as 2 bytes, the bottom byte, the C byte, is going to be the byte that we've read in from the sprite that we want to show to the screen. It doesn't really matter what the B byte is. All that really matters is B plus 0 is the first byte and B plus 1 is the second byte. So as I say, we've got to be aligned to a 256 boundary so that it could start at hexadecimal 1000 or hexadecimal 1100, hexadecimal 1200, that would all be fine, but it can't start at 1080 in hexadecimal because that wouldn't be fully byte aligned. Now the command in WinApe is align 256, in VASM it's align 8, very annoying, but that's the difference. So this is working in individual bytes and this is working in a number of bits, so that's why those are different there. It's a little bit annoying. Anyway, our first lookup table is going to have 2 entries for the 256 possible bytes that could be read from the sprite, so we need 512. The second one, which we only need if we're doing mode 1, will have 4 entries, so that's a full 1024, which is quite a lot, but as I say, we're trading memory for speed, which is often the sacrifice we make. Now, when we build these lookup tables, we actually need to understand the format of the screen mode we're working with and how the bits in those bytes actually correspond to individual pixels. Now, in mode 1, there are 2 bits that make up the leftmost pixel, the one here and the one here. And the pixel next to that is made up of the one here and the one here. And the last pixel on the right-hand side of the byte is made up of the bits here and here. And these are effectively kind of like bit planes. The top nibble and the bottom nibble make up the number that defines the color that that pixel has. Now, our byte will have 4 pixels in it. And if we're doubling the size, we'll need to take 2 of those pixels and basically double them up so that the byte is filled, and we'll have to create another one for the remaining 2 pixels of that byte that we're scaling up, and that's what we're doing here. So we're getting 1 pixel here and we're storing that in C, and we're getting the other one here. Then what we're doing here is effectively shifting this one along. We're then ORing in the pixel we got here, shifting it along again, ORing it in here, and this is effectively moving the pixels along and then doubling them, and that is creating a byte that is filled with the stretched version of the 2 original pixels. So that is the first byte in our lookup table, and then we're inking H because we're now going to create the second byte in the lookup table for the other half of the byte, and then we're taking the third pixel here with these 2 bits and the 4th pixel here. We're then shifting those here and here, and we're ORing them, and that is filling the entire byte with those 2 pixels, effectively doubling the size. Now, we need to repeat this 256 times, so we're starting with B0 and we're incrementing it until it reaches 0 here. So that will repeat around until we've done 256 entries there. That will fill the first lookup table, and then we're doing the same with the second lookup table, which has of course 4 entries per source byte. So we're calculating the 2 bits here. We're then filling the entire byte this time, so we're shifting each pixel 4 times, ORing it each time, filling that entire byte with that pixel, doing the second pixel here, third pixel here, 4th pixel here, and we're repeating there for the 4 times lookup table. So that's how we build our mode 1 fill there. Of course, if you were doing this on the SAM Coupe or the ZX Spectrum, you'd need to do different patterns because you would need to understand how the bytes of the screen correspond to individual pixels. As I say, this is how the CPC works. I can't entirely say I'm a fan of it, but this is what we have. I prefer the MSX style, where the 2 neighboring bits do an individual pixel, but this is what we have. It's not the end of the world. Now, the mode 0 is even weirder. It's opposite bits that define a pixel. That's the way it works. Ironically, it's actually quite handy for this kind of thing because we can just do 1 bit shift to move a pixel from the left-hand side to the right-hand side, and that's what we're doing here. So there we're defining the first byte here. So effectively, we're taking the byte that would have 2 pixels in mode 0, and we're taking one of them and then copying it to the other so that they're both filled in, and then we're doing the same for the second one here. And that's filling our LUT for the mode 0. And as I say, we only need the 2 times 1 because for the 4 times 1, well, those bytes are filled in both with the same pixel anyway, so it doesn't make any sense to have a second lookup table. As I say, we just use each entry in the 2 times lookup table twice to scale up to 4 times, and we could do the same for 8 times and so on. And that's really all there is to it. I mean, it's a trick with lookup tables. We've used them before for other things, like we use them for flipping sprites and for transparency. Lookup tables are kind of a necessary evil. They're very fast, but they're trading memory, and that's usually what you end up doing. But I think if you need to do big sprite scaling in any reasonable speed, I mean, if it's just a title screen, it doesn't matter how long it takes to draw, possibly. But if you were doing anything in actual gameplay or anything where it was more time sensitive, then I think this is probably your only realistic option for horizontal scaling. Now, of course, we can only do 2 and 4 times. We can't do 3 times here or 2.5 times or anything. That would be much more complicated. I'll be honest, I can't think of a way of doing that would be sufficiently fast to doing the gameplay. I mean, I'm not saying there isn't one, I'm just saying I'm not smart enough to do it. So if you can think of one, please feel free to suggest it. Write your own tutorial on it by all means. As I say, I'm not saying it's impossible, just that I don't know. What I would probably do if it was me and I wanted some in-between frames is I'd make a slightly bigger version of this sprite or a slightly smaller version, and then I'd use these to scale in between versions. I'm actually writing a game at the moment which does have some, shall we say, 3D depth to it, and I was originally considering using this for that game, but that game has other quite significant technical complexities to it, and I don't think I can take any more, to be fair. So it's not going to be in there, but it would have. I was considering it, and maybe if I start feeling it especially masochistic, I will put it in there. But as I say, I think it's a fun little thing, and I think it's certainly worth looking at, if just to remind everyone the potential of lookup tables for speeding up graphics work when you want to do something that would otherwise be quite slow. Anyway, there we go. That's the end of this tutorial. I hope you've found it interesting. I think it's been a bit of fun. If you've liked what you've seen, of course, you can like and subscribe and go ahead and get the source code from the website. It's always on the website. It should always be on the website. And if you can't find it, that's a mistake. So please tell me about it, because someone thought I wasn't putting them all on there. They should all be on there. So yep, go ahead and grab that and do whatever you want with it. Anyway, I hope you've enjoyed this. Thanks for watching. If you've liked what you've seen today, please consider backing me on Patreon. Every video I make takes about 5 to 10 hours of development, research and documentation for the website, so it really takes a lot of time, and it's only through the continued backing of my patrons I'm able to keep justifying putting the time in, to be honest. So if you are interested, you can support me on there. I release my videos to the Patreon backers way before regular YouTube viewers, and also when questions come, I always prioritize the Patreon backers when it comes to requests and suggestions and things. Although of course all my videos do come out to non-Patreon backers eventually, because I do consider them to be an educational content that really everyone should have access to. But as I say, if you want to support me, you can do so on Patreon. Links in the description below. Also, I now have a Teespring store, so if you want to buy some Chibi Akumas or Learn ASM merchandise, you can go ahead and find something on there, and I'll probably be releasing some new designs if people seem interested in it. Anyway, whatever you do, thanks for watching today, and goodbye.